Welcome back to our channel, where we take you on a journey to the very edges of science and beyond. Today, we're diving into one of the most profound and mysterious concepts in modern physics, quantum vacuum energy. Imagine a hidden ocean of energy, existing everywhere and at all times, even in the most empty voids of space. It's an idea that challenges our understanding of reality and could potentially revolutionize the way we think about energy and the universe itself. But what exactly is quantum vacuum energy? And is it something we could ever harness to our advantage? Buckle up, because this is going to be a deep dive into the strange and wonderful world of quantum physics. Let's start by setting the stage. When we talk about the vacuum of space, what comes to mind? Most people might picture an absolute emptiness, a void devoid of matter, particles, or energy. But in the world of quantum mechanics, even the most seemingly empty space isn't empty at all. Instead, it's filled with something known as quantum fields, which are constantly fluctuating. These fluctuations represent the lowest possible energy state of the universe, a kind of restless, seething energy that exists everywhere, even in a perfect vacuum. This is what we refer to as vacuum energy. The concept of vacuum energy arises from the principles of quantum mechanics, the branch of physics that deals with the behavior of subatomic particles. According to quantum theory, particles are not just points in space. They are excitations of underlying quantum fields that permeate all of space. Even in the absence of particles, these fields are never completely at rest. They constantly fluctuate due to the inherent uncertainty in the quantum world, a phenomenon known as zero-point energy. These fluctuations mean that the vacuum isn't truly empty, but rather filled with a chaotic sea of virtual particles popping in and out of existence. This leads us to an astonishing conclusion. If we apply the equations of quantum mechanics to these fields, we find that the amount of energy in the vacuum should be infinite. Yes, you heard that right. An infinite amount of energy in every cubic meter of space. This might sound like an absurd notion, but it's a direct consequence of the fact that these quantum fields can vibrate in an infinite number of ways. Every point in space can theoretically contain an infinite number of vibrational modes, from the tiniest quantum fluctuations to massive oscillations, all existing simultaneously. But this is where things get complicated. If there's an infinite amount of energy filling every bit of space, why don't we observe this energy directly? Why isn't it affecting our everyday lives in a noticeable way? To answer these questions, let's explore an ingenious experiment proposed by Dutch physicist Hendrik Casimir in 1948. The Casimir effect is a phenomenon that arises when two uncharged, parallel metal plates are placed extremely close together in a vacuum. According to quantum theory, the quantum fields between the plates are restricted in their vibrations because the space between them is so small. This limitation means that there are fewer vibrational modes between the plates compared to the space outside them. The result? There's a tiny imbalance in the vacuum energy, with more energy outside the plates than between them. This imbalance creates a pressure that pushes the plates together, a force that can be measured and observed. This is the Casimir effect, and it's one of the most fascinating manifestations of vacuum energy. The fact that we can measure this force provides strong evidence that vacuum energy is real and not just a theoretical construct. However, the Casimir effect also highlights a fundamental challenge. Although we can observe the effects of vacuum energy, we cannot easily extract or utilize it to do work. The reason we can't tap into this vacuum energy lies in its very nature. Vacuum energy represents the lowest possible energy state of the universe. To extract usable energy, we need a difference in energy levels, much like how a water wheel requires a flow of water from a higher elevation to a lower one. But with vacuum energy, we're already at the lowest possible point. There's no lower energy state to move to, and thus, no way to extract energy from this ground state without violating the fundamental laws of physics. To make this concept clearer, Imagine you're in a building and you're trying to go down to a lower floor, but you're already at the ground floor. There's nowhere else to go down. The same principle applies to vacuum energy. It's like being at the ground floor of the universe, with no basement to descend to. Any attempt to extract energy from this state would be akin to trying to make an elevator go below the building's foundation. It simply can't be done with our current understanding of physics. So, where does this leave us? Despite the tantalizing implications of vacuum energy, we currently have no practical way to harness it for energy production. The Casimir effect, while fascinating, doesn't provide a method for generating new energy. It merely redistributes the existing energy within a system. But this hasn't stopped scientists and science fiction writers from speculating about the possibilities. In the realm of science fiction, the idea of using vacuum energy as a nearly limitless power source has captured the imagination of many. From powering starships to creating advanced propulsion systems, the potential applications of harnessing vacuum energy are as exciting as they are speculative. However, these ideas remain firmly in the realm of fiction, as they currently defy the known laws of physics. That said, our understanding of quantum mechanics and the universe is still evolving, and it's possible that future discoveries could change the way we think about vacuum energy. One of the most significant mysteries in modern physics is the discrepancy between the amount of vacuum energy predicted by quantum mechanics and the amount of vacuum energy we actually observe in the universe. In the late 1990s, astronomers made a groundbreaking discovery that the expansion of the universe is accelerating. The most straightforward explanation for this acceleration is the existence of a mysterious force known as dark energy, which is thought to be related to vacuum energy. However, when scientists calculate the amount of vacuum energy needed to explain this cosmic acceleration, they arrive at a value that is astonishingly small, around 6 x 10 to 10 joules per cubic meter. This is a far cry from the infinity predicted by quantum mechanics. This discrepancy, known as the vacuum catastrophe or the cosmological constant problem, is one of the greatest unsolved problems in physics. On one hand, quantum mechanics suggests that the vacuum should be filled with an infinite amount of energy. On the other hand, observations of the universe on a cosmic scale suggest that the vacuum energy is incredibly tiny. So, what's going on here? The truth is, we don't know. This is a puzzle that has baffled physicists for decades, and solving it could lead to a profound shift in our understanding of the universe. One possibility is that our current theories are incomplete. It's possible that new physics, beyond our current understanding, is waiting to be discovered. Physics that could reconcile the apparent contradiction between quantum mechanics and cosmology. For example, some theories suggest that the vacuum energy we observe is just a tiny fraction of a much larger hidden energy that exists in extra dimensions or parallel universes. Others propose that the vacuum energy might be linked to the fundamental structure of space-time itself, with implications that go far beyond our current understanding. Another intriguing idea is that vacuum energy could be related to the mysterious concept of quantum gravity. Quantum gravity is the theoretical framework that aims to reconcile general relativity, which describes gravity on a large scale, with quantum mechanics, which governs the behavior of particles on the smallest scales. If we could develop a successful theory of quantum gravity, it might help us understand the true nature of vacuum energy and how it fits into the larger picture of the universe. But even if we do eventually solve the mystery of vacuum energy, it's not clear that we would be able to harness it for practical purposes. The challenge of extracting usable energy from the vacuum is immense, and it may require entirely new technologies or breakthroughs in our understanding of physics. However, the potential rewards are equally immense. If we could find a way to tap into the vast reservoir of vacuum energy, it could provide a nearly limitless source of power, with implications for everything from space travel to clean energy here on Earth. In the meantime, scientists continue to explore the mysteries of vacuum energy, both through theoretical research and experimental investigations. The study of vacuum energy is closely related to other cutting-edge fields of research, such as the search for dark matter and the study of the early universe. By probing the nature of vacuum energy, we may gain new insights into some of the most fundamental questions in physics, such as the origin of the universe, the nature of time and space, and the ultimate fate of the cosmos. One exciting area of research is the study of vacuum fluctuations and their effects on particles and fields. For example, scientists are investigating the possibility that vacuum fluctuations could influence the behavior of particles in ways that we haven't yet fully understood. These investigations could lead to new discoveries about the nature of quantum fields and their interactions, potentially opening up new avenues for harnessing vacuum energy. Another promising line of inquiry is the study of the relationship between vacuum energy and the concept of entropy. Entropy is a measure of disorder in a system, and it plays a crucial role in the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease. Some physicists have suggested that vacuum energy might be linked to the entropy of the universe, with profound implications for our understanding of thermodynamics and the arrow of time. As we continue to explore these and other questions, one thing is clear. The study of vacuum energy is a frontier of modern physics, where our understanding of the universe is constantly being challenged and expanded. The quest to understand vacuum energy is not just about solving a theoretical puzzle. It's about exploring the deepest mysteries of the cosmos and pushing the boundaries of human knowledge. So, where do we go from here? The journey to understand and potentially harness vacuum energy is likely to be a long and challenging one, but it's also a journey filled with excitement and possibility. As we continue to explore the frontiers of quantum mechanics, cosmology, and other fields of physics, we may uncover new principles and technologies that could change the way we think about energy and the universe itself. In the end, the study of vacuum energy is a testament to the power of human curiosity and the relentless drive to explore the unknown. It's a journey that reminds us of the vastness of the universe and the infinite possibilities that await us in the realms of science and discovery. Whether or not we ever succeed in harnessing vacuum energy, the quest to understand it will undoubtedly lead to new insights and breakthroughs that will shape the future of science and technology. As we wrap up this deep dive into the mysteries of quantum vacuum energy, we leave you with a question. What do you think the future holds for our understanding of the universe? Could we one day unlock the secrets of vacuum energy and use it to power our civilization? Or is this a mystery that will remain forever beyond our grasp? Let us know your thoughts in the comments below, and don't forget to subscribe for more mind-bending explorations of the universe's greatest mysteries.